Hey, so this is my Programming Challenge 4 code. This in particular is just some shared um, classes and a function for numbers 10 and 11. So I just have a state class here, which doesn't mean anything because I didn't think there was any um, information about differentiating a state from another one besides that it's a different state. Um, except that with the transition function, but that's not anything that the state needs to class needs to store. So that brings me to my finite automaton class. Just a mathematical definition: states, start, final states, input alphabet, and function. This just preserves the preserves this. So the Cartesian product of the states and the input alphabet is the power set. So this just initializes them all to the empty set. And then I update that based on what I got in here. So this doesn't need to be, doesn't need to have all of those transitions to empty set. And I just store that information, and then here this print function from Programming Challenge 2 and 3. It's just modified a little bit. So we have our finite automaton, and then this name. This is just supposed to be a dictionary that will convert the state object, or that given the state object will yield a unique name for that one, so that I can print that down here. So it's just, if not, then I'm just going to generate that, which is just going to assign an S whatever number for each state, and then the start state is going to be S0 and the other one's S1, S2, etc. So I print here. So for transition in the transition function, if there were actually is a transition there, or if it's not the empty, if it doesn't transition to the empty set, then I'm going to print it out. That's this here, and this name dictionary I'm using here because this is a state, the current state, and then I'm just using this dictionary to just give it the name. And then I just print the starting state and final states, and this piece and this piece just generate the sets based on the whatever the each case, it's a set of states, and I'm just converting it to the names of all those states for printing purposes. Okay, so here's number 10. So I just import this. This program takes a regular expression and generates a finite automaton to recognize the strings, which is the language of that grammar. So I just have a few functions here based on the ones in the book. This recognizes nothing. This recognizes lambda, or this finite automaton, because I'm returning a finite automaton in each case. And then this recognizes a single character, this input character. This one is the concatenation. So I didn't follow exactly how the book described it, because I could make some assumptions on the nature of the automaton, because I knew it would be generated by one of these functions. So these comments explain most of this pretty well, I think. And then the union here of those two, again, I made some assumptions, and this explains this for the most part. So Then we have the client closure. And this one, we create a new, or no, we just take the start state and the states we already have, the final states we already have, and then we add the initial state, because if it's a client closure, then lambda belongs to that, or is part of the language. And then the same inputs, but then I just say here for old plus, so the old transitions, plus for every start state, 2 states, so every transition from the start state, we're going to transition from the final state to, from every final state to whatever state that is, on the same input, of course. And then this one, this code just generates the finite automaton. Oh, oops. Yeah, this is a regular expression, not a regular grammar. Okay, so this, I have this function in here which converts it to a list of lists to take care of the parentheses. And basically what this does is, if there's nothing in there, then it'll return the automaton that doesn't recognize anything. If there's lambda, it turns lambda. If it's just a single input, it'll just return the finite automaton that recognizes that input. If it's a union, it will return the union of the two, of recursively, whatever this function comes out to, of each of these parts. So then I have this piece here, this automaton list. So it's just for each character in this regular expression now, which will not include unions or lambda, or be as just a single input or FD. Then if it's a star, we're going to update the previous one to the client closure of that. And if it's not, then we're just going to just generate the automaton that recognizes that piece, and then we're appending it to the list. And then this one, if it's a star, then we're just editing the previous one to be the client closure. And then here, I just start with the first piece that I have there, and then for all the others, it will just concatenate until it concatenates everything, and then it'll return the automaton. So then this just takes care of parentheses, similar to what you want in 5, I think. I don't think I need to go into this much, but this is just, as we're building, this is what it's going to return. This is like a stack, which takes care of, whenever you create parentheses, we create a new list inside of this list, and then put everything in until we reach everything that we get until we reach the closing parentheses. And then this just keeps track of which list we're supposed to go back to once we get out of that. And so, yeah, and this is just whatever current list we're in. So that's that. And then here, I just define my special characters, and then just use them in here. I just I explain the input, get the input, and then we're just going to, as long as we inputted something, then it's going to generate the FA based on the parsed regular expression. So that just takes care of parentheses, and then we're printing it, and then we get more input and try again. Okay, so we can run this. Have this example here. You can try your own. And we see here all these transitions, starting state, final states. I checked it. This is correct. And you can change it and do different ones if you want. So that's 10. And now 11. We're just importing those functions again. And then I just explained it takes the productions of a regular grammar and then generates a finite automaton to recognize it. So in order to make the input symbol, I just say S denotes a start symbol, and then we just have applies and this denotes lambda, comma, separate productions. So it's like this. This is from my programming challenge 1. They're almost the same. And then this is get my input and parse it a little bit. And then as long as we did get input, we're going to take care of this. I mean, this is similar to what I did before. Non-terminal / state names. This will just take all the non-terminals out, because based on their position, given that this is a regular grammar, I know that any of these on this side and any of these, that the second characters are going to be non-terminals, and the other ones are going to be terminals. And then I just create these dictionaries to convert those strings, those characters, into states, and those states back into those characters. Okay, so yeah, and then input, set, final states, and then here I just correct for lambda, and then here I get the set of states, the states of so you take the characters, and then I just create a finite automaton with these basic things. This will just populate the function with those default transitions to the empty set. And then after that, I will add the transitions taken literally from these productions. Each one of those is a transition other than this one, which initial starting state is a final state. So then I create the finite automaton, and then I print it, and then I get more input to keep going so you don't have to restart your program. And use so to print this, as you can see, these I use the letters based on those two dictionaries to denote the state names, so it makes it easy to follow. So state C, input for state A, and then in these cases I just created a final state, and that shows up here. And then because we have this production, this is the start is also a final state, and then you can put in more if you want. And